Namaskar. Welcome to Prakasham Basics. I'm Prakash Zog. Science keeps coming up with new discoveries, new areas, new methods of understanding what is happening around us. But it is this technology which puts these scientific discoveries to use for the use of the good of the man that helps him to do things better, more efficiently, and so forth. All this has happened even in the household lighting that we are talking of. Uh, in the recent years, we've come up with LEDs. This is a recent method of illumination. Cheap, far more efficient, very durable, easy to use, very close to white light that we know of, and operates pretty fast. Um, if required, it can provide you with all other colors also. So, what are LEDs? To understand them, we must understand a little bit of science and a little bit of technology from where it has come. And it's important because both these terms in science that I'm going to talk of today and the technology I'm going to talk of is applicable in a number of areas all around us. So whenever we talk of those, we need to understand and grasp what I have been talking of today. LED, light emitting diode. So it must give out light, and for that it must use electricity. And a diode is something that has two electrodes. Di, so two. uh, and it is based on using something that has two electrodes but is made of semiconductor. We need to understand what semiconductors are if we have to go ahead a little bit. We have wiring that is there in our houses which was made out of copper and nowadays out of aluminium. All these are good conductors of electricity. All metals are good conductors of electricity. And we have the coating on top, which is an insulator, which is a bad conductor. Uh, it could be plastics. We have wood as bad conductor, diamond as bad conductor, sand, silicon, SiO2, that's and ceramics and so forth. All these are all bad conductors. So we have the good conductors, the bad conductors, and in between the two of them would obviously lie what are neither very good, neither very bad. So semiconductors related to electricity, obviously. Uh, Silicon and germanium are the two pure form semiconductors that are known to us as elements. There are other organic ones also. We have anthracene, one chemical. We have some forms of special ice that's also semiconducting. There are some organic semiconductors also. And then there are mixtures that result into semiconducting also. What is all this? To understand this, let's look into a little bit of chemistry. There's a guy called Mendeleev, and he arranged all the elements in a particular order, which is known as the Mendeleev's periodic table. And he made a number of columns, and then they got modified, and we now have roughly around 18 columns that are available. Uh, what we are interested in is in the 13th, 14th, 15th type of elements. Um, but they are also special. They are typically third group, fourth group, and fifth group elements. Uh, it's something that you must have heard of, that's all. The fourth group elements are silicon and germanium. That are actually, you also have carbon and silicon and germanium and tin and lead as all those of the fourth group. Then there are some that are short by one electron. These are typically of the third group element. Boron is one of them. You have aluminium also there, gallium, indium, and so forth. So there are some elements on this side which are of the third group. Then there are some with one electron extra. They are naturally the fifth group element, which are phosphorus, and you have some others, bismuth, antimony, you have arsenic, and so forth. Uh, all these are fifth group. They are all supposed to be extremely pure. If the material is extremely pure and it behaves like a semiconductor, It is known as an intrinsic semiconductor. But you don't keep it pure. You add a little bit of impurity to it and make it a far better semiconductor. Here, surprisingly, the word semiconductor and impurity has a different meaning altogether. The impurities put in this have to be extremely pure. And whatever is added to another substance in a very small proportion is an impurity according to chemistry. So, if you have lead and if you have add 1 micron of a little bit of gold in it, then gold is impurity. So same way, what you do is you take silicon or germanium, nowadays typically silicon, and add a very small amount of either a third group element or a fifth group element. How much? 1 part in 10 raised to 8. That's 10 million. This is the way it is measured. So, and one of the technical terms some of you all must have heard is ppm, parts per million. So that's the small fraction in which this impurity gets added on. When this impurity is added, the substance becomes far better semiconductor, and it becomes an extrinsic semiconductor because the impurity has been added. But it could be either from the third group or the fifth group. If you add the fifth group, one electron becomes extra and electrons are negative. So this type of a semiconductor is then known as a N type of a semiconductor. And if you add a third group element, one electron falls short in the whole structure as it gets arranged. So this has an absence of negative. So it's known as a hole. And this hole is as good as a positive. So adding these impurities makes the system either P type of semiconductor or N type of semiconductor. Okay, so what you have now is the original block, which has been, let's say, converted into P type of semiconductor and N type of semiconductor. The consequence is that the electrons' energy levels will have changed because of this addition and subtraction. So the levels become different. And so this has excess amount of electrons and this is short of electrons. There's a little bit of neutralization. Let's not go into that. That's known as the barrier potential, but let's keep that aside. Um, so this makes two parts, P type, N type. So you provide an electrode this side like my remaining part of the arm and the remaining part of the arm here. So there are two electrodes and these are the two semiconductors, P type and N type, and they're joined to each other. But the levels inside are slightly different. Now this then is a typical semiconducting diode. There's a difference in energy. Now, let's say you apply a certain voltage and the electrons begin to flow. So the electron comes up to here and it then moves on to the next side. So when it goes to the other side, it jumps over. And as soon as it jumps over, whatever extra energy that it had, it will give away as it jumps to the other side. Simple. It's like these people who climb up the stairs and dive from the diving platform. And so when they get down, fall into the water, there's a splash. So the higher they are, the more splash there will be. And that's exactly what I talked of even some time back during tube lights. This is that energy gap that is overcome. And the electron jumps down and gives out its excess energy in terms of a photon, that is a light particle. And it comes out. If this photon or a light particle that is given out or a wave that is given out is something that we can see, then that diode, whenever current begins to flow, will result into light coming out of it. And that then is a light emitting semiconducting diode. Short form is that LED, light emitting diode. So use it and what you get is light out of it. It's not that simple. So we must know a little bit of history of what really happened. Uh, Around 1962, the earliest form of diodes were made. But the materials were not really as good as we can make them today. So naturally, the energy gaps were not really very high. So the photons that came out had very small amount of energy difference. And so naturally, they were in the low energy area. That is energy less than red. And that is typically infrared light. So it's not visible. We can't see it. So these are IR diodes, infrared diodes. We can't see them, the light that comes out of it. They're still used to a very large extent. All our remotes work still on these IR diodes. So if you look at your remote, there is a small bead like diode that is there, you can see in the front. And when the battery gets weak, the amount of energy available to the electrons becomes weak, and so the infrared radiation can't be enough to trigger on or switch on the TV or switch off some device because of that radiation that is going ahead. So those are those IR diodes that were earliest developed and still equally well used today. Uh, then the next attempt was to try and get an energy gap which would be closer to giving out white light. A lot of attempts were made in this. And instead of using just silicon and adding impurities, they started mixing the third group elements and the fifth group elements, making compounds, semiconductors. And they came up with a lot of other possible combinations. Uh, this resulted into certain semiconducting diodes, which started giving out light in the visible region. The earliest of these were made out of GaAsP, and it contains gallium and arsenic and phosphorus. The people who did this earliest were the one of the laptop companies that is so famous, HP, and they are the ones to put them to use the first time around 1969. And all these were typically those reddish diodes that were made. The earliest one I remember in my physics department, Professor Bede had brought was a Wang 90 something laptop, and we were all fascinating looking at the light that was coming out of those small LEDs, something like this shade, with all letters. And these letters are all made out of 7 bits. These are known as 7 segment displays. And HP was the first one to bring about all these 7 segment displays. Seven because you have one, two, three horizontal lines, one, two, three, four vertical lines, and using that you can make all the figures 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth. And so that's how display started off. The Japanese were very keen on putting all this technology to use. They put them in watches, and the earliest LED watches, the red ones, I'm sure some of you all must have seen long back, uh, many years ago. Uh, then came a lot of effort to try and shift from red to other colors. And the Japanese, as I said, Koreans put a lot of effort in all this. And the Japanese came up with gallium nitride type of semiconducting material. And that started giving out blue LEDs. And once these blue LEDs were made, there was a big change. So see what happens. I have a yellow sheet, and behind it I put a red, I'm sorry, a blue uh, semiconducting diode. So it gives out blue light. It passes through, like what I talked of in case of tube lights. The energy is transferred, and what comes out is not only the yellow light, but since there are situations available, the part of the blue light also comes out. And if you have a combination of yellow and blue, the two extreme ends available as far as this visual spectrum, not exactly the end, but close to the end. So you get a combination which is practically as good as white light. So what you need is a yellow phosphor and blue diode behind, and what you get is practically white light beyond. A lot of attempts were made to find out what is the best possible phosphor in microscopic particle sizes that can be mixed so that part of the light from the phosphor will come out and the rest of the blue light will also come out. And they hunted around for material. They came up with what is known as a YAG, YAG, yttrium, aluminium, garnet. These are extremely small particles that were made in powder form, and they were mixed plastics and polyurethane and so forth. And then what you had is a YAG surface through which the blue light used to come out, and then it used to result into white. So YAG plus blue is as good as white that we could obtain. Um, in fact, if you look at a broken LED bulb, you would see those small diode chips inside, and they are typically of that yellowish green shade when the system is off, and that color is typically of the YAG doped system. This YAG was also used in YAG lasers. I'll come to that long time afterwards sometime when I talk of lasers. Uh, so one method was to use this YAG plus blue, resulting into the light that came out. And since many other colors of diodes were also available, there was an idea to encapsulate all the three together, red, green, and blue together, and pass current suitably among all three of them in such a manner that the combination emitted a light which was closer to the shade that you wanted, and you could get possibly whatever color you wanted, or if all of them were of equal intensity, it would practically give you white light. So using uh, triple diodes and using blue and YAG were the two techniques. This triple technology fell back a little bit. It is still used. I'll come to that sometime later on. But what we need and what we use today very often is this other form. The when off, yellowish, and when on, bright white. That's the one that we need to talk of. Now, how is this LED made? It's pretty simple. One thing, you don't need too much of material. So even if you feel that technology of extremely pure silicon and pure germanium and pure other materials, the industry and the setup is extremely costly. But once you start manufacturing, the whole thing becomes dirt cheap. So what you do is to have a very small dot of a p-type and an n-type of semiconductor, connect very thin electrodes to it, encapsulate the whole thing in a epoxy or a polyurethane mixture with the YAG powder, and shape it like a small bullet, a round-headed bullet, and have the two electrodes coming out from below. And what you have is a simple diode. Nowadays, of course, these are the typical ones that are used at different places. But when technology started going further, they made all this into horizontal surfaces. And so there is a flat material, let's say like this. You have a pair of electrodes, electrode coming from here, and then there will be a next one and a next one and next one and next one. Where do you put them? On a surface. And on the surface, you have conducting wires. So this became the technology by which the diodes were manufactured in long strips or on circular boards. This is SEMTech, um, surface electrical mounting technology and technique, and it results into long strips of these diodes, all connected to each other by very small microscopic wires, either immediately on top itself or from below, either way around, depends upon the way it is used, or small discs. So if you break open a bulb, what you see inside is all those bits that are there inside. And these are the semiconducting diodes, and they're connected to each other, and they are all dirty yellowish green color. The instant you switch them on, they start giving you white light. There's a hitch in all this. These semiconducting diodes all work on DC, direct current. And what we have at home is AC. And this is 220 volts or 110 as I'm sitting here outside India. So that's going to be too much for the semiconducting diode, which actually requires close to about 3 volts or 6 volts or 12 volts, depending upon how it is structured and how many of them are put in line and so forth. So you can't connect them straight away to and plug them in. So you need a special method, which is a step down transformer to reduce that 220 volt to the 5 to the 6 volt or 12 volt and convert it to DC, AC to DC. And that's exactly what your battery eliminators do, or your chargers do. They take that 220 or 110 and convert it to 5.6 volt or 6 volt that is available to charge your laptops or your mobiles and so forth. Instead of putting it there, you connect it to a bulb, and if you can get a very large amount of current, you can switch on all of them and get the necessary light. So what do? You have that disk on which all those are mounted. By the side, you have this rectifier made out of semiconductors itself that is also added along. And finally, the two terminals that come out in a holder that is and unit that can be put in a bulb holder straight away. And you put the whole thing in a white shell, translucent, and this becomes your LED bulb. Instead of that, you put it on a strip, encapsulate the whole thing, or slide it inside another cavity made out of white transparent plastic. Uh, Put the two ends, make it of the standard size of 4 feet or 2 feet, and what you have is a LED tube light. Because the rest of the circuit is put in the cavity below and the two wires are taken out. And so what you have is only two wires. So you just plug them into the socket by attaching a pin, and it becomes a LED tube light. So that's how the technology came forward. And these have a lot of advantage. One, they use very little current because the amount of conversion is more than 50%. There is obviously some amount of heat that is created because of also the transfer from blue light to yellow light. All that uses up a little bit of energy, and the whole system gets to hot because of that rectifier and so forth. And there is some loss. So still getting more than 50% efficiency in all of them, as compared to the 5% that we started off in ordinary bulbs. So 7 to 8 times more amount of efficiency is available, times light is available. And in the beginning, when they started off, compared to that, as today, the LEDs can give roughly 10 million times more amount of light than the earliest type of LEDs that started off. So see, there are so many advantages. There is no choke, there is no starter, there is another circuit that is inside. Um, all that makes the whole thing very simple. The required voltage is 6 volt or 12 volt, and if you're not going to use it at home, you can use a couple of batteries and make a torch out of it. And see the advantage. You have extremely bright LED bulbs that are used in torches nowadays, which throw a big sharp beam of light. And all these are far better than the torches that we used to use long back. So all that semiconducting technology has been put to use to produce this lighting that we use at home today. A 20 watt LED lamp is as good as a 150 watt halogen lamp as far as light output is concerned, roughly around. So you would find, see, so much of advantage is there. And that is why all lighting gradually is shifting to LED type of lighting. Technology is going to take us beyond this also sometime. What comes about is something for us to think of later on. Many combinations of compound semiconductors were used. Gallium from one side and phosphorus from the other. Gallium from one side and antimony from the other. Gallium, indium from one side and phosphorus from the other side, third group and fifth group. That indium is not found in India. It's Indiana State University, and their research was done, and finally that element was discovered. So that's a different area we'll talk of sometime. So we have so many different elements whose combination results into these light emitting diodes. Some of them are used there itself. Some of them are organic based diodes nowadays, semiconducting diodes. And instead of semiconducting diodes, you have organic type that are also being put to use in TVs and so forth. And this is all new technology that has come out of the original semiconducting ideas, leading to LEDs, which have nowadays they can start off with about 3 volt, and another system that will have a chain of them giving you a number of bright lights around. All these are based on LEDs, light emitting diodes, a part and parcel of the illumination that is all around us. Knowledge itself is also an illumination. If you have liked whatever I have said, please pass on this information to your friends. Tell them about it. When you look at an LED lamp next time, realize the technology that has gone behind all this. Something that triggered off in around 60s, got modified in about 70s, and countries like Japan, Korea, and China set up major industries to make LED bulbs, a technology that has been made so cheap and so much available to everybody around in this world. That's what technology is supposed to do. Sahana bhavatu, sahana bhunaktu. Let us all progress together. Like and subscribe to this channel. Till we meet again with some more information on science after 15 days. Namaskar.